Thanks, Letitia. I also want to draw your attention to the lecture on Monday, which is going to be something special. Dr. Caroline Fennikiak, who's done a lot of research on the subject, you'll see it in the newsletter. I can highly recommend this, so don't miss this. It's a creative session par excellence. Okay, I'm going to start recording this. First of all, I want to welcome Johan Retief, Admiral Retief, the former head of the South African Navy. Those of you who have attended our sessions in the hall, you will know the wonderful lectures he's given us in the past on naval incidents and various things at sea. And we also have the fortuitous position of having another admiral who's also retired here in Manus, who has also given us some wonderful lectures on the sea and navigation and all that. So, Johan, thank you very, very much for all that you've done for us, for the preparation. I'm really looking forward to this morning's session. Over to you.
Good morning, everybody. I trust you can hear me clearly, Gert, or tell me if you can't hear me.
Yeah, as you're fine.
Can you voor my camera afskakel?
Ek sal, ja, okay. Toe maar gaan we aan.
We're going to look at the longitude problem as it existed in the 18th century and before that, and the way it was solved. On this slide that you're watching now, you've got a picture of myself 30 years ago. Yeah, that is no verkeerd geweest. You've got a picture of myself 30 years ago. I don't look the same anymore. In the center, you have a picture of the globe. On it, you have lines drawn from the North Pole to the South Pole. These lines are called meridians. And you've got lines running east-west, and they are called parallels of latitude. Now, the meridians have all the same characteristic in that the plane of the meridian passes through the center of the Earth. And you can see they're distinctly not parallel to one another. In the case of the parallels of latitude, there's only one parallel of latitude that has its plane passing through the center of the Earth, and that is called the equator. All the other parallels of latitude are smaller than that. Now, a circle whose plane passes through the center of the Earth is called a great circle. And other circles, like other lines of latitude, are called small circles. There used to be a trick question for navigation students that said, how many degrees are there in a great circle? And the answer is 360. And then the next question is, how many degrees are there in a small circle? And so many people answer 180, which of course is wrong. In any case, we are going to talk today about the lines of longitude, the meridians, and as far back as Eratosthenes in the 3rd century before the Christian era, he understood the requirement for fixing a place by some other means on the world. Hipparchus carried on with the idea, and Ptolemy in the 2nd century after Christ went further with it and started creating a system of meridians and lines of longitude, lines of latitude. Now, this thing was driven to a point in 1707 when the Sunni naval disaster took place, and I will tell you more about that. On the picture at the bottom right, you see a number of British ships on the rocks, which is a terrible place to be. Okay. Just to recap on the Sunni naval disaster, it took place on 20 October 1707. The British fleet returns from Toulon, the year of the Spanish Succession War, 1701-1714. 21 ships, 15 ships of the line, and 6 smaller vessels sailed from Toulon back to England. They were commanded by Admiral of the Fleet Sir Claudius Shovel, who had his flagship in HMS Association. 3 ships of the line and 1 smaller vessel went aground on the western banks of the Scilly Isles at about 8 p.m. on 20 October 1707. HMS Association sunk in 4 minutes. Between 1,400 and 2,000 British seamen were lost. Now, if you look, let me just get my pointer. They had a position roundabout over there when they crossed the 100-fathom line, 200-meter line, which they sounded, and they knew how deep the water was, and they knew approximately where they were. They managed to get another site later on, and a latitude 4940 north, and that gave them the idea that they were in line with the entrance of the channel. But they were not. They didn't know what the longitude was. There was no way of determining that at the time. But the wind was good, and they aimed for the entrance of the channel. They missed, and they hit the rocks. You know, an old sailor used to say, going aground can spoil your whole day. It did in their case. There are 2 legends about this that may be of importance. The first one is that one of the sailors in HMS Association actually warned everybody that they were in the wrong place and they were going in the wrong direction. He was allegedly accused of inciting a mutiny and was hung from the yardarm summarily. The second legend that goes around is that Admiral Shovel, in fact, was still alive when he was found on the islands. 2 ladies found him. In those days, the Scilly Islands were a rough and ready place, and they made a lot of store by picking up bits and pieces that washed ashore. Admiral Shovel wore a beautiful emerald ring on his one hand. The ladies assisted him towards the pearly gates, and then they took the ring. Rumor has it, or legend has it, that at the deathbed, one lady confessed to it, gave the ring back to the cleric that attended to her at the death, and he sent it back to the family. But the ring was never found again. Okay, to continue. Many years before that, the Dutch astronomer Gemma Frisius was the first to ascribe how an accurate clock could be used to determine a longitude. He said, if only one could accurately measure the time the sun passes your meridian, and you had a timepiece that accurately displayed the time at the Greenwich meridian, then one could just read off your longitude from the timepiece. As simple as that. Now, terminology, I'm going to use the words mer-pass. Meridional passage is the time that the sun passes over your meridian. A meridional altitude, or mer-alt, is the sailor's way of describing the altitude of the sun or a star that passes your meridian. Angles was measured from the deck of a ship by means of an octant on the left or the sextant on the right. This was designed approximately in 1731 by Mr. John Hadley on the right. And it was used for measuring the angle between 2 objects from the deck of a ship. The latitude was obtained in those days by measuring the altitude of Polaris, the North Star, also known as Alpha Ursae Minoris, the brightest star in the constellation of the Little Bear, or the altitude of the sun at mer-pass, when it passes over your meridian. Now, in the southern hemisphere, Polaris is not visible. And I've only once sailed a ship, in fact, to Toulon in my life, and I could never identify the North Star. I tried to take a stellar observation of the Polaris, but I failed. I've since become a better astronomer, and now I would find it. Any case, so how did it work? Here you see a circle in the northern hemisphere, and the idea is to show you how latitude is obtained from the North Star. This vertical circle is the plane of the observer's meridian. The observer is right in the center of the diagram, and right above his head is a point called the zenith. And 90 degrees to the zenith, if you look left and right, you will see the horizon. The distance between the zenith and the equator corresponds to the observer's latitude. And 90 degrees from the equator is the star Polaris at what is known as the North Celestial Pole, NCP. Now there are two right angles involved here. The angle between the equator and Polaris, and the right angle between the horizon and the zenith. If you take your sextant and you measure the altitude of Polaris, you can see it on the right, you can say that the latitude corresponds exactly to the altitude of Polaris. Unfortunately, it's not quite true. There are some corrections you must make. There's a declination correction, because the declination, the distance between the celestial equator and Polaris, is not exactly 90 degrees. It's in fact 89.20 something degrees. So you have to make a small correction there. There's also a correction for parallax, because you're not sitting in the center of the system, you're standing on the surface of the Earth. And there are also refraction and dip corrections. Dip is to do with your height of eye above the horizon. But for all intents and purposes, it's very simple to obtain your latitude by taking an observation of Polaris. Keep in mind that you can only measure this angle at sunset or sunrise, when both the star and the horizon are visible. If it's too light, you can't see the star anymore, then of course you've got a good horizon, but you can't measure the altitude. And if it's still too dark, then you can't see the horizon in your octant or your sextant, and you can't measure the altitude. So this is a measurement that can only be taken during what is known as nautical twilight, the time just before the sun rises or just after the sun sets. Here's an indication of how the latitude can be measured from the altitude of the sun, known as the meridional altitude, MAOT. Once again, the vertical circle is the plane of the observer's meridian. Right at the top is the zenith, and at 90 degrees to the zenith is the horizon. The south celestial pole is on your right over here, and the sun is over there. By measuring the altitude of the sun, you can find out what your latitude is. Look at the following angles. From the equator to the zenith, from the equator over here to the zenith is your latitude. From the equator to the sun is the sun's declination, which changes from 23.5 degrees south to 23.5 degrees north. In this diagram, the sun is south of the equator. And the angle from the horizon to the sun is called the altitude of the sun. Okay, and the latitude then is equal to 90 degrees minus the altitude, which is that angle, plus the declination, or minus the declination, depending on whether the declination is north or south. So a very simple calculation, but of course this can only be done at MAPAS. So measuring the latitude is only possible early in the morning, later in the evening after sunset, and at Milpas. Only those 3 times of the day. Let's continue. We go back to Gemma Frisia's words. If only one could accurately measure the time the sun passes your meridian, and you had a timepiece that could accurately read the time at the Greenwich meridian, then one could just read off your longitude from timepiece. Now, when you say this, you must keep in mind that it's possible to denote longitude in terms of time. Let me flip back to that one. In the case of astronomy, we measure a star's north and south as declination, but we measure its east and west or its longitude in something called a right ascension, which is measured in time, hours, minutes, and seconds. Similarly, on the Earth's surface, you can measure longitude in hours, minutes, or seconds, and in fact, it was done in the good old days of the early 19th century in that way. To determine accurately Greenwich Mean Time, a gentleman called Tobias Meyer, his pictures on the right, produced excellent tables on the moon's position. Based on his work and the fact that the angle between the moon and another bright celestial object is the same from any position on the Earth, a set of tables could be produced whereby, when this lunar distance is measured, the time of the Greenwich meridian could be deduced. This slide is out of context. I'm sorry, I'll come back to that. The lunar distance method, once again, here you see a picture of the moon, and in this case, on to the right of the moon, a bright star, Regulus, Alpha Leonis, the brightest star in the constellation of the Lion, and the angle between them is measured. This angle is called the lunar distance. Now, anywhere on the Earth at this moment of time, this angle is the same. So if you've got accurate tables in your nautical almanac, you could take the angle and immediately go to the nautical almanac and say that when I took this angle, the time was that. However, the moon does a full circuit against the background of the night sky in 27.3 days, which equates to 13.2 degrees per day or half a degree per hour. In fact, those of you living in the south part of South Africa, if you looked it up this morning just before sunrise, you could see the moon and Venus in close proximity. Yesterday they were 12 degrees apart, today they were closer together, and tomorrow morning they will be about 13 degrees apart. The lunar distances were tabulated in the Nautical Almanac from 1767 to about 1906. So any ship with a good nautical almanac and a good sextant could measure the lunar distance and thereby determine a good approximation of Greenwich Mean Time at that moment. In 1714, Parliament, after the investigation into the disaster at the Scilly Islands, enacted what was known as the Longitude Act. This act provided a public reward for such persons or person as shall discover the longitude at sea. The act offered a series of awards. If you could determine the position or the longitude within 1 degree, it was worth £10,000 at the time. Within 40 minutes of arc, £15,000. And if it was within 1 degree or 30 minutes of arc, £20,000. These amounts were recommended by Sir Isaac Newton and Edmund Halley to the Parliamentary Committee. There were subsequent acts which ordered further awards to do with navigation. I must tell you that 20,000 pounds in the 18th century was a vast amount of money. And whoever won the prize could have called himself the Bill Gates of the 18th century. The marine chronometer, let's think about it. On the diagram, on the photograph on the right, you will see Harrison's marine chronometer as he had it in 1772. John Harrison, picture on the left, took 31 years to design and make an acceptable marine chronometer. He was by trade a carpenter, and he was also a very good clockmaker. And his first clocks, he used wood to design and make the escapement. Later on, in his chronometer, or his sea clock as he called it, he used a grasshopper escapement instead of a pendulum. Now, ladies and gentlemen, a pendulum is a good way of measuring time when you're standing on solid ground. When you're on a ship that rolls and pitches, the pendulum just doesn't work. So he used a balance called a dumbbell or grasshopper escapement, which you can see on the right, with two dumbbell balances. It took Harrison 5 years to make his first sea clock. It was not very accurate, but he was supported by Edmund Halley. He made another one, and that didn't work well. He made a third one, on which he spent 17 years, but he did not achieve the required accuracy. One of the problems on this clock was the fact that if the ship should turn as it tacked or veered or went about, the movement sideways acceleration actually changed the running of the escapement. And so the clock became more and more inaccurate as you traveled at sea. Later on, he realized that a mere watch needed just to be made sufficient accurate to be able to do this job. It took him another 7 years to construct a sea watch. And on the right, below a picture, is a photograph of his first sea watch, which he called H4. It was tested in 1761 on a voyage from Portsmouth to Jamaica, and it fared very well. The Longitude board was not convinced and said it was just luck. See, the moment it comes to paying out money, the Admiralty lost interest. A second trial was made of the same watch, and this time Naval Magellan, the current astronomer royal at the time, who actually very well supported the lunar distance method and drew up the nautical almanac, went along to assess the accuracy of the watch. During this assessment, the watch was found to be considerably more accurate than the lunar distance method. Once again, the watch performance was assigned to luck, and the Admiralty did not wish to pay the money. They also claimed that it was too complex to make and too expensive. John Harrison, who was feeling the pinch after all these years, turned to King George III, and he gave him his watch, and the king personally tested the watch, and he found it to be sufficiently accurate. The king supported him and gave Parliament to push in the right direction, and John Harrison was given the money that he won. Okay, now let's look at the whole problem from the angle or view of the longitude lines. Here you see the globe, North Pole at the top. The dark blue line running north-south is the Greenwich meridian. The light blue lines are 15-degree gaps measured towards the east and measured towards the west. These are all meridians. Longitude was obtained by comparing Greenwich Mean Time or the local mean time of Merpas. In other words, if you measured Merpas and it was at 10 o'clock, then you say that is by longitude. It was expressed in hours, minutes, and seconds at that time, or later on, it was converted to an angular measure, which meant that time had to be multiplied by 15 degrees. Now, this is important, the fact that it's converted to an angle. The moment people became clever enough to calculate the position of stars by means of spherical trigonometry, they had to work with degrees and minutes and seconds. You couldn't work with degrees and minutes and seconds in latitude and hours, minutes, and seconds in longitude. It's a case of apples and pears. So everything had to be converted to apples. The problem was, when exactly does Merpas take place? Because on a ship, it's very difficult. If you look at this diagram on the sun on the 4th of May, I took this for the sun in a position in Sandown Bay. Now, all of you know Sandown Bay is the bay between Manus and Kleinmond. And I selected it because it's very close to where I live. In any case, it's very difficult to determine exactly when over here the sun crosses your meridian. But some bright spark came up with an answer. What about measuring the time from here to there? And you call it, this method, a short equal altitude, and then getting the average between the two. Who discovered the short equal altitude method? I couldn't figure out. In any case, let's look at the situation. On the 4th of May, at 10 hours GMT, somebody measured the altitude of the sun and was found to be 39 degrees 10 minutes. They then waited for the sun to come down again on the other side. And once again, they kept the sextant at the same altitude. And they measured the time. And they found that time was 11:04:08. Now I converted it to decimals. 1016.01 converted to 10.2662 hours. We call that T1. And 11.00689. We call that T2. Calculation of Merpas, time of Merpas is T2 minus T1 divided by 2, average amount, plus T1. Calculation is done over there, and we work out that the sun actually passed at 10:40:05 over our meridian. But this is not the local mean time of Merpas. Life is not that easy. This time corresponds to solar time, the time the actual sun passed over our meridian. And we have to apply the equation of time to get to the right problem or the right answer. Now, how does this work? There are two problems we have to face. The first is the obliquity of the Earth's axis. There you see the plane of the meridian once again, the south celestial pole. My apologies. South celestial pole at the north, at the top, and the north celestial pole at the bottom. I nearly said the south. The yellow ellipse is the ecliptic, the apparent path of the sun around the Earth. Where the ecliptic crosses the equator, we have the equinox, the closest one to us being the September equinox, and the one on the other side of the Earth, the March equinox. Why is the Earth upside down? Because it's in the southern hemisphere. Okay, and then where the ecliptic touches the meridian, on the left is the December solstice, and on the right is the June solstice. Now, if you project the sun onto the equator, you will find its speed varies according to a sine curve. It's pretty much close to, the error is pretty much close to 0 here. 0 there, 0 there. Oh, my apologies. The other problem we have to face is the eccentricity of the Earth's orbit. The Earth in December is closer to the Sun than it is in June. Now, Kepler's second law says, Kepler's laws for planetary movement said a line segment joining a planet and the Sun sweeps an equal area during equal times. Here you've got short legs and a fast movement. Here you've got long legs and a slower movement. In December, the Sun moves at about 20,287 kilometers per second, and in June, 29,288 kilometers per second. And you have to allow for this as well. If you create curves out of it, this curve that runs in a sine curve is due to the obliquity of the Earth's axis. This other curve, this one over here, dot dash curve, is due to the orbital speed of the Earth around the Sun. If you combine these two curves, you get the red curve, which is an indication of the speed, the difference between the solar time and local mean time. You take this graph, and this graph is presented in form of a table in the Nautical Almanac. Here, if we take around about May, we will find that when we took our problem, it was about 3 degrees fast. We then apply this correction to the equation of time, to the GMT of Mopos, solar time plus minus, in this case, 1040 plus 3 minutes, which gives us 1043.05, which we know then is our longitude expressed in hours, minutes, and seconds. To change it to degrees, we need to multiply it by 15, and you can then subtract it from 180 to get 19.23 degrees. Thus, the longitude is east 19 degrees 13.48 seconds. Let's visualize this quickly. Once again, we go to the Earth. We know that the longitude can be measured in hours. Here you see the Earth with the meridians in accordance with the hours as measured on the clock. 12 is on GMT, or the reference meridian. 1300 is to the west of the meridian. 1100 is to the east of the meridian. On this side is sunrise, and on this side is sunset. Here you've got the GMT of Mopos as we measured it, and we know that it was 1043.05. So 1043.05, and that is our longitude as we measured it with a clock. We can do the same by looking at the longitude as measured in degrees, minutes of arc. Longitude 19 degrees, 13 minutes, 48 seconds. Once again, the red line, red meridian, is that of our longitude. Once again, if the GMT of Mopos is more than 12 degrees, it's to the west, and other way around, it's to the east. Okay, one of the things I must address is why an octant changed to a sextant. An octant was made an arc of 45 degrees to measure celestial bodies above the horizon. And no celestial body can be higher than 90 degrees, really. 90 degrees and a bit, maybe due to dip. Once you started measuring the lunar distance, you may exceed 100 degrees between the moon and another celestial body, and a longer arc was required. Hence, the sextant was designed and made and replaced the octant. Nowadays, the octant is not used at all. Now we come to, where did the money go? Longitude Acts, and I say Acts because there was more than one act. It was de-enacted during the 19th century. John Harrison eventually got 23,065 pounds, which really made him quite rich, a multi-millionaire in today's currency. Munch developed a marine timekeeper, got 3,500. Tobias Meyer, who worked out the lunar distance tables, was given 3,000 for his efforts. Thomas Earnshaw, for design improvements to the marine chronometers after Harrison, was given 3,000 pounds. Charles Mason, 1,300 pounds for various contributions to Meyer's lunar distance tables. Kendall for copying improvements made to the stopwatch, sea watch, got 615 pounds. Arnold, 300 for incremental improvements to this timepiece design. Fuller, 300 pounds for the contribution to the lunar distance method. And Nathaniel Davies for design of a lunar telescope for Meyer. One of the things I must tell you about lunar distance, you could actually do the same calculation by taking the time the moons of Jupiter is occulted by the planet. And by looking at that, we will all over the world that can see Jupiter at the time will see the occultation at the same Greenwich Mean Time. Why was this not used? You can't put the telescope on a ship, it rolls too much. So that did not work from a point of view of the ship. And I come to the end of the talk, bibliography. I used the Admiral Manual Navigation, Bowden's American Practical Navigator, the Handbook of Spherical Astronomy, and Wikipedia. This, ladies and gentlemen, is the end of my talk. However, I want to show you something else. My next talk is the 21st of August 2020. Here you've got a picture or a etching of HMS Beagle in the Strait of Magellan. It is going to be the subject of that talk. What is important, Beagle in its second voyage was sent to survey the whole world from a point of view of longitude. Because the captain's loneliness on board, he was allowed to take a guest with him, and he advertised for such a person who could give him some background scientifically, and a young naturalist, geologist, applied for the job and went with the ship. It was a 5-year voyage, and the young man who went with him was Charles Darwin. Thank you very much indeed. I'm open for questions.
Excellent, Johan. Thank you very, very much. What a complicated affair, really, to find out where you are on the Earth. Why didn't they just use GPSs in those days?
Those days, the GPS were too expensive. They couldn't afford it, especially not.
Oh, is that the problem? I see. Can I just add one little thing? Maybe it's just too obvious to say, but let me say it anyway. The reason why the pole star was used is because the axis of the Earth passes almost through the pole star, so therefore it's stationary in the sky, or more or less stationary for a viewer on Earth. Is that correct?
Quite correct. Let's get back to the pole star.
And the problem is that we don't have a similar position in the southern hemisphere. I mean, as we know, the point where the axis of the Earth passes through the sky in the southern hemisphere is halfway between the Southern Cross and the star Achenar. But there's no bright star in that position. So you've got to do something else in the southern hemisphere. Is that correct?
Yes, you can't. In those days, you could not use another star, really, because even Achenar and Canopus were quite far distant from the pole.
Yes.
So you just use the sun.
Yeah.
But
Well, that is why Polaris is so convenient, because the axis of the Earth passes almost through it, and the correction you talked about is because the axis is slightly off the center of Polaris. Is that correct?
Correct. The declination should be 90. It's in fact 89 point something.
Yes. Yeah.
And of course, the fact that we don't have a south star will be considered by some as discrimination against the southern hemisphere.
And the next point I want to make, which is also a very obvious thing, I'm sorry for raising it, but my engineering mind works that way, is because the Earth rotates east to west, and obviously not north to south, it's easier to determine the latitude because it's fixed in space, whereas it rotates, and therefore you need all the other things you were talking about, the clock and all that, to determine the east-west longitude. Is that correct?
That's quite correct. And that's why when we do astronomy, you also need a clock to determine the right ascension of a star or the moon or the sun.
Yeah. Okay, thank you. That was my question. Anybody else want to ask a question? Just press down your space bar or raise a hand, either way. Anybody else? I see Fatsa, your microphone is open. Do you want to ask a question?
And Phil's got a question.
Okay, go ahead, go ahead. I'm not sure who that was.
Phil, you've got a question.
I had two questions. The first was how do you estimate the sun? When is the sun at its zenith? And Johan's covered that. The next question was, when you're using a sextant and you're taking your measurement from the sun, how do you protect your eye from looking directly at the sun?
That's a very, very valid question. Most sextants, even in those days, had filters put in the path of the light traveling from the mirror, which is where the sun is, to the telescope. And you could flip down, on a modern telescope, you can flip down 4 filters to make it quite dark. And you had filters on the mirror that looks at the horizon as well. Because if the sun is fairly low down, the light coming from the sea is also quite bright. But the filters on the line of the horizon is less intense than the filters for the sun. And you normally only have 2 filters for the line of sight. I can in fact flip to the, here you can see a sextant. There are the filters for the path of the light coming from the mirror, from the sun, to this mirror, to that mirror, to the telescope. And there you have the smaller filters for the horizon, known as the horizon filters.
Anybody else? I see, John, your microphone is open. Do you want to ask a question?
I heard just thank goodness for GPS.
Yeah.
No,
Donald,
thank you.
Donald, I see your microphone is open. Did you want to ask a question?
Yes. The only question which has partially been just mentioned was, in this modern age of space, can't a much simpler technology be used by putting in a satellite somewhere?
You want to respond to that, Johan?
I'll try to. The way I understood it is, can't you put a satellite in the position of the South Pole star? Satellites have to orbit the Earth to have to stay up in space. If you stop orbiting, they fall down. Satellites in geostationary orbits are 31 or 35,000 kilometers from the Earth, and they're not bright enough to be seen from the Earth. Satellites that are any closer will be orbiting, and it's very difficult to see. So even the GPS satellites, which is at 20,000 kilometers, you can't see. So no, satellite doesn't solve the problem from an astronavigational point of view, but from a satellite navigation point of view, they work very, very well.
Thank you.
Any other questions?
In fact, the accuracy of satellites is such that they are currently considering putting up a GPS constellation for the Moon and for Mars to be able to fix the position of future landers on those bodies. And lo and behold, it may even happen.
Yeah.
Yes, go ahead. Go ahead.
How do we access the recording? You know, if I want to try and understand what Johan said a bit better, because it's quite complicated for me being non-mathematical. So I want to go over it again. How do I do that?
The recording has been placed on the cloud, and anybody is interested in receiving the recording, I can forward to you the access code that you can download it or watch it directly from the cloud storage. So anybody who's interested in the recording, let me know, and we can send you the access code for the cloud storage.
Thank you.
I have a question.
Go ahead.
It's more about inferences, because I've been following this topic, but more from an African astronomy view, and they mostly focus on the measurement of time and not longitudinal. And I want to find out, are there any inferences between the two?
I'm not quite certain I understand the question, but let me explain it very briefly as follows. Because the Earth rotates around its axis with time, the Sun, the Moon, the planets, all are seen to be moving around us. Now we know they don't move. We're in fact the one that moves. But the point is that time can be measured with the sun. If you've ever heard of a sundial, you will know that if you put the sundial down, as the Earth rotates, the shadow on the sundial, the shadow of the gnomon or pointer of the sundial, will slowly move from the west to the east as the sun rises in the east and goes over to the west. And that can be measured with a fair degree of accuracy. But keep in mind, you have to apply the equation of time. And normally on a good sundial, you will have a little table saying in January add so much, in March add. So you have a way of correcting that. But the sundial is the normal way of measuring time if you don't have anything else.
So could that explain?
Answer your question?
Yes, to a degree, but I want to find out if that could explain how they managed to navigate in ancient Africa.
I believe that when it came to navigation on the Earth in ancient Africa, people actually observed the stars in the time that they were up there. And they know, for instance, if in January, Orion, the constellation of Orion arises in this angle, on this direction, then they're about here. Because as your position changes, so the position of rising, of setting, of constellations will change. Remember, the constellations don't move. They're not like the sun and the moon. Because that was the way the ancient Polynesians navigated when they sailed across the Pacific Ocean.
Fatsai, the Chinese also drew maps as they sailed from China, particularly to the African coast. They used a system of knots, you know, a rope with knots in it. And they threw that in the sea and took the time that they passed a certain number of knots. And they estimated the speed that they were traveling on the sea. The trouble is that the sea also moves because there are sea currents. And based on that, they drew maps. But if you look at those maps, you see that they're completely distorted because they were not able to accurately measure, in fact, how fast they were sailing because they didn't know how to, well, they didn't have clocks, and they didn't know how to compensate for the sea currents. So it's the same problem that Johan was talking about. Unless you have a clock on board, you cannot determine your longitude accurately just from observing the sky. And this was the whole issue that Johan talked about. Sorry, Johan, you probably know more about that than I do.
This is important. I'm not always certain what people have in their minds. In the good old days, when I was a young officer, navigating along the Namibian coast was very awkward because the coast was very low down, it was sand, it did not reflect on radar very well. And we used the system of taking sun lines. For instance, the time of Merpass will give you a latitude line. At the same time, you took a sounding of how deep the water was. And if you went to the chart and you consulted the soundings on the chart, and you know that the water depth is 150 fathoms, you can go along the 150 fathom line, and you can take the latitude line that you got from the sun, and where the two cross, you have what we call a fix, a position line, point of position. So even in the days of Sunni disaster, they also use soundings to try and find how far they have been up on the Merpass line. Okay.
Can I say one more, relate one quick story, Johan? When you talk about a sextant, I often think about the phenomenal story of Shackleton. After he was shipwrecked and they landed with all their crew on Elephant Island and on Antarctica. He took 5 men with him, there were 6 of them, on a small boat, and they sailed for 800 miles from Elephant Island to South Georgia Island on this very rough sea. And despite the cloud and the rough sea and the smaller boat, they were able to use a sextant to navigate across the sea for 800 miles. I still think that was a phenomenal achievement to be able to do that.
I think so too. I presume he also had a watch. And I presume he also had a nautical almanac, because those are kind of going hand in hand with the sextant. It's very difficult without that to do the job.
So would a sextant be, I'm not sure if you've read about this stone called the Lebombo stone in Swaziland that they used to navigate. Would that be similar to a sextant?
Yes. You can measure against a physical object the altitude of a star or the sun. In fact, if you go and look at the old observatory of Tycho Brahe in Denmark, he used physical arcs built out of brick with lines drawn on them. And you would peer along the line and these buildings were made in a north-south direction. So you could see at exactly what height a star passes this line. So using a physical object is very much something that is used. And of course, people today think that Stonehenge and similar structures had a lot to do with determining when was Midsummer's Day or Midwinter's Day or whatever. And that such a arrangement of stones, in fact, functions as a type of sundial.
And then I have a follow-up question.
Yes.
You mentioned something about the moons of Jupiter. Would those be visible from the naked eye?
No, they're not visible to the naked eye, but they are visible through a good binocular. They are visible through a good binocular. Yeah.
There's mention of also in ancient Africa astronomy. I forget the place because it's in West Africa, but they claim that they used Jupiter to navigate the I don't know where they were going.
Okay, two things. Legend has it that the sun had such good eyesight, and of course, in those days there were very few street lights. It was very, very dark, and if they're fairly high up, the atmosphere was very clear, that they could actually see the brighter moons of Jupiter by the naked eye. I'm not certain. I have tried to. I can't see them. With my telescope, it's very easy to see them, like clear as a bell. But Jupiter can also be used for navigation purposes. In fact, the three naked eye planets, a naked eye planet is a planet you can see with your naked eye. Venus, Mars, Saturn, and Jupiter are all used for navigation. My apologies.
Thanks, Fatai. Any more questions?
No, I'm done.
Anybody else?
Just Letitia again, just to say thank you to Johan. Fascinating as usual. I can't wait for the HMS Beagle. Thank you very much.
And Johan, from my side too, thank you very much. And thank you for all of you who have joined us, and particularly our visitors from East London, from overseas, from New Zealand, or the geologists. Thank you all for joining us this morning. Johan, this is it. Thank you very much. All the best. And thank you, Henny, for recording this thing. Anybody who wants access to the recording, send me an email and we'll forward the codes to you. All the best. Goodbye, everybody.
Okay,
Thank
bye.
you.
Goodbye, Gert. Goodbye, everybody.
Thank you, Johan.
Yes, thank you.
Thanks, John.